In this video, we're going to talk about linear inequalities as opposed to the linear equalities that we talked about in a previous video. So let's start off with an equality. I know I'm emphasizing that, but I'm doing it intentionally. We're going to start off with an equality, and then we're going to see how much of it can bring forward to the inequality. Because what you want to do when you're learning different topics is you want to try to reutilize any steps that you've already committed to memory and that you already understand, and bring those forward and just add to them in this specific case, as opposed to learning entirely new approaches for each one. Let's see how much we can reuse, all right? So let's look at inequality, and we had 4 times 3x plus 5 equals 6 times x plus 1. Now this is an equality because it has an equals. If we had an inequality, it might be something like 4 times 3x plus 5 is less than 6 times x plus 1. Okay, not strictly equals to. Here we go. So let's do the equality. Remember our steps. We simplify the left-hand side, simplify the right-hand side, get our x's or whatever your variables are isolated on one side, constants on the other, and then you divide or multiply in order to find out what one of the variables is, like a 1x or 1y. So let's simplify the left. Now we use your rule of order of operations. We look inside the parentheses. We can't add 5 to 3x, but we can multiply by going outside because we don't have exponents. So 4 times 3x is 12x. 4 times 5 is 20 equals, can't add 1 to x because they're not like. 6 times x is 6x. 6 times 1 is 6. Right? So what we've done is we simplify the left-hand side. I'm going to abbreviate that to LHS. Then we simplify the right-hand side, which we did both as we went through. Then we isolate our variable terms on one side and isolate our constants on the other. Then we do whatever we need to do to get a 1x, what one of them is, all right? So I have 12x on the left, 6x on the right. Let's isolate them, and isolate means to get them by themselves on the left side. So that means we do not want them on the right. So we do the opposite of what they're currently doing in order to remove it, okay, negate it, make it go away, however you want to say it. And we do the same thing to the other side to be legal, right? Because what you do one side, you have to do the other. So 12x's minus 6x's leaves me 6x plus 20 equals 6. Now, if my variable terms are going to be isolated, they are the only thing on that side. If you're isolated in a room, you're the only one in the room. So the only one on the left-hand side should be 6x. So the opposite of to add 20 is to subtract. So 6x is, and 6 minus 20 is minus 14. And when I want to know what just one x is, I don't want to know what 6 x's are. I want to know what one of the x's is. We look at the 6 and it is currently multiplying. So to negate it, I do the opposite, which is divide by 6. And I'd have x is negative 7/3. All right? Now, you know how to do that. And you can check these. You can put that back up into x and see if that's correct. Let's see what happens over here. So you would do the same thing, and we're going to go a little faster since we just went through all the rules. So can't add 5 to 3x, can't add 1 to x, but I can multiply. So 4 times 3x is 12x. 4 times 5 is 20. It's less than 6 times x is 6x. 6 times 1 is 6. So then we would want to isolate our variables on one side, constants on the other, So I'm going to put them on the left, so I do not want them on the right. So I subtract them because they're currently added. So subtract over here to be legal. Keep it balanced. 12x minus 6x is 6x. If I want the variables isolated on the left, that means they have to be by themselves. So the opposite of adding 20 is not subtracting 12, it's subtracting 20. So 6x is less than negative 14. X is less than negative 14/6, which reduces to x is less than negative 7/3. So it looks like all the steps are exactly the same. I mean, because we did exactly the same. And for 90% of the problems, that's probably true. We're going to do the exact same thing. Simplify the left, simplify the right, isolate our variables on one side, isolate our constants on the other, then get a 1x. Okay, now what's the difference between these two? There's two main differences. When you check x is equal to minus 7/3 up into here, you get one answer. You check it one time because there's only one number in this case that makes this a true statement. When you look at this one, there's an inequality. And we're going to talk in a minute about how do you know this is less than. This says any number that's less than negative 7/3. So let's see. Negative 7/3 is negative 2 1/3, right? 3 goes into 7 twice with 1 left over. So any number less than negative 7 should work, all right? Well, that could mean that x being minus 3 would work. Okay, x being minus 4 might work. X is minus 3.5, minus 4 7/8, minus 1,000. All of these would give you a true statement. Just to show you, we're just going to look at a couple. If x is minus 3, right, then you would go, what happens with this? 4 times 3 times minus 3 plus 5, less than 6 times minus 3 plus 1. So 4, we work our way from the inside out. 3 times negative 3 is negative 9, plus 5 is less than 6. Negative 3 plus 1 is negative 2. 4 times negative 9 plus 5 is negative 4. So is negative 16 less than negative 12? That's my question. Is this a true statement? Think about your bank balance. Isn't negative $16 less than negative $12? So yes, that checks. How about x is negative 4? 4 times 3 times negative 4 plus 5 is that less than 6 times negative 4 plus 1. So again, 4 times 3 times the negative 4 is negative 12. Negative 4 plus 1 is negative 3. 4 times negative 7 is that less than 6 times negative 3. Is negative 28 less than negative 18? Yes, as far as your bank balance. So think of it this way. The process so far has been the same. The answer, no, because in an equality, typically you get a solution, a number. And that is the only number that's going to make that a true statement. Every once in a while, like we talked about in linear equations, you get something that's true all the time. It's an identity or, and so all real numbers would work, or sometimes there's no solution. But if you get an answer, a numerical answer, it is only one answer. If you get a numerical answer per se on an inequality, there's a whole string of numbers that would work for you, right? Now, so the first difference is you don't just get an answer, you 90% of the time get a whole slew of an infinite number of answers. Now, what are the other things that you might have to think about an inequality? Well, one, let's talk about how to say it, right? If you have something like 3 is less than 5, you know that algebraically because you know 3 is a smaller number than 5. But what if it was just an x? And how do we know to say less than or greater than? So I've heard all sorts of things, from people say that, this is an alligator, this is my bad alligator drawing, okay, and that it eats the larger number. I don't know if your teacher told you that in your past at any time. Whatever it is that helps you to understand it, then if you understand it, stick with it. All right. The way I do it is like this. If we read left to right and we have this little arrow like this is the more narrow end, the smaller end. This is the wider end, the larger end. So if you read left to right and you hit this smaller end first, you say less than. If you read left to right and you hit this wider end first, you say greater than, right? Using that process, you can read left to right or right to left and you still get the same statement. So looking here at x, you read left to right, you hit the smaller side first, so you say x is less than 5. If you read right to left, which sometimes you have to do, you would read 5, you hit this wider end first, so you would say greater than x. Let's look up here. If 3 is less than 5, 5 is greater than 3, right? Reading either direction. Okay. If negative 3 is less than 5, 5 is greater than negative 3. If 5 is greater than 3, 3 is less than 5. Those are all true statements, correct? Now, if I multiply by a positive, like we did in the example earlier, and let's just pick 2. 2 times 3, 2 times 5. This was less than, right? Let's see if we've changed the intent of the problem. 2 times 3 is 6. 2 times 5 is 10. 6 is still less than, right? 6 is less than 10. 2 times negative 3 less than 2 times 5. Negative 6 is still less than 10. Okay, it looks different, like when we multiply both sides of an equality, it looks different, but the truth is still the same, right? It's still less than. 2 times 5 greater than 2 times 3. This is 10. This is 6. Yeah, it's still greater than. Okay, so the truth stays the same. What happens if we multiply or divide by a negative? And we'd have negative 2 times 3, negative 2 times 5. So negative 2 times 3 is negative 6. Negative 2 times 5 is negative 10. Now, is negative 6 less than negative 10? Think about your bank balance. Is negative $6 worse than negative $10? No, it's not good, but it's not as bad. So negative 6 is greater than negative 10. So it flips, it reverses. It's no longer less than, it's now greater than. Multiplying by negative 2 here. Negative 2 times negative 3 is positive 6. This is negative 10. Is it still less than? No, it is not. So it reverses. Negative 2 times 5, negative 2 times 3. We had a greater than, right? This is negative 10. This is negative 6. Is it still greater than? Nope, negative 10 is less than negative 6. So when you multiply or divide by a negative, you have to remember to reverse the inequality. Now, who exactly is going to remind you to do that? No one but you. All right. So the two things that are different about an inequality in its essence are we're not going to get and expect just a singular answer. We're expecting a range of viable numbers that would all make this a true statement. And you have to remember that when you multiply or divide by a negative, that you are going to reverse the inequality. So over here on our little list of statements, you can use the same statement you had, but right in here where you're getting ready to multiply or divide by whatever to get a 1x, you're going to have to make a little extra note for you to follow that says if you multiply or divide by a negative, you reverse the inequality. Okay, and some people put it in there as a note before they actually do the process of multiplying or dividing, and some people put it in there right after that as a check saying, did you multiply or divide by a negative? You would decide where you want that because this is your list. All right, so let's try another problem. And let's try negative 2x plus 1 is less than 5. So here we go. Simplify the left. I can add 1 to negative 2x. Simplify the right. There's nothing to do. Isolate your variables on a side. Well, all my x's are on the left, so let's leave them there. That means I don't want the plus 1, so I do the opposite to negate it. And I must do the same thing on the other side to keep the scales even. All right, so negative 2x is less than 4. Now, I want to know what x is. That's my goal. So I'm going to multiply or divide in order to get 1. I could multiply by a negative 1/2, or I can divide by a negative 2, since negative 2 is multiplying. The opposite of to multiply is to divide. I have to divide the other side by the same thing to be legal. So these two reduce or cancel depending on who your teacher is. So some teachers are violently opposed to the word cancel. Some don't care. All right. A positive 4 divided by a negative 2 is a negative 2. But here's my question. Is it still less than? Would I get full credit if I left it like this? No, because right here you multiplied or divided, you divided in this case, by a negative, and you are the only one that's going to remember to reverse this inequality. No one's going to remind you. So this has to be clear in your mind. Now, this is inequality notation. All right. Sometimes they have what they call set builder inequality. So this is set builder. Let's talk about this for just a second. Both of them are saying the same thing. It's sort of like a fancier way to say a sentence versus a kind of plain way to say a sentence, right? So let's look at inequality. Just says any x is bigger than a negative 2 will make this a true statement. So negative 1, negative 1/2, 0, 1/3, anything like that. This is saying the same thing with a set builder, but let me explain to you what this means. So these little curly braces like this are mathematically translated to for the set. Okay. And then this x that's right here is of all x. This part right here is such that. And then you have x is greater than negative 2. Okay. So when you read this, when you start right here, you would say, for the set of all x such that x is greater than a negative 2. So it's just a fancy way of saying, hey, the numbers that are greater than negative 2 are the numbers that I want. Now, when you did these, and you probably did these somewhere in, I don't know, elementary school, junior high, somewhere in there, you also would graph them, and they would give you a number line, like this. And so here would be 0, and negative 2 would be over here. And depending on the book, depending on your teacher, depending on how long ago this was, one of the possibilities is you would draw a little bubble right here. And you would say, do I color in the bubble or do I leave it open? Well, since this says greater than only, it did not have equals, right? Then it's left open. And the x's that are greater than negative 2 are to the right. These are all the numbers that are greater than negative 2. So if you had greater than or less than, you left a little open bubble. if you had greater than or equal to or less than or equal to, you colored it in. Okay? And now they have another notation where if you would have colored it in, there you're going to use squared off brackets that could go either direction like this, or you're going to use round ones like this. So another way to show this one is you would use a curve as opposed to an open circle, and then have your arrow go right down on top of the graph. Now, I've seen a lot of computer programs do that, when it's grading your homework and it has these choices for you to have where it's already pre-drawn for you, and they'll have this lovely different colored um, arrow right on top of it, something like that where you can clearly see it. If you're doing it pencil and paper, you're going to turn it into your teacher, and bless them if they are actually grading pencil and paper homework, because that takes so much time, and but it gives them an opportunity to interact with you and see how the class is doing. So I applaud the teachers that do that, and you should thank them for taking the time to do that, because bless their hearts, they're working hard. All right, if you do that, please don't do this. I had a student do this for me one time, and I was just like, all right, y'all. And I had said, I don't care which notation you use. And so this would be their variation of it. The only reason I knew they were at -2 is they actually wrote that where I could see it. And it looked like that. Now, can you barely see the arrow and barely see the little curve? And I'm over exaggerating their arrow. I actually had to get a magnifying glass to see anything that even looked like an arrow. All right. So y'all, please take pity on your teacher's soul if they're grading, all right, and make it obvious. I actually like this one because I can actually see what you're doing really quickly as opposed to having to squint. All right. Now, this is graphical. All right. And then they have what's called interval form, which if you're going on in math becomes kind of the main version, right? So as you go on, and even in this class, most of the books and probably most of the teachers I've worked with, and I've worked with several hundred, um, is they start to fall back on this interval form as sort of the main one. All right. So here we go. So I want the x's that are from -2. So you write left to right. I start at -2, and all the way down here is positive infinity. So I'm going to go from -2 all the way to positive infinity from your point of view. It's this way. All right. I never get to stop at infinity because I always keep going and going and going and going and going. And I am not including the -2. So this is curved. And the nice part about this is the fact that, if you're typing this in, it's easier to do this -2 and 8 with the little parentheses than it is trying to do this set builder notation and even the inequality. All right, especially if you do, greater than or equal to. Trying to get that in there is a little bit more clunky. All right, so these all mean the same thing. You doing okay? I hope. All right, let's do another problem. So if we have 8x minus 3x plus 2 is less than 3 times x plus 5. So simplify the left. All right, I could subtract 3x's from 8x. That would be 5x. Simplify the right. Can't add 5 to x, but I can multiply. So 3 times x is 3x. 3 times 5 is 15. Now I want my x's on one side. I want to isolate them on one side. Isolate my constants on the other. And I think most people tend to put their variables on the left either all the time, or they put the variables on the side where it's going to end up being positive so they don't have a negative variable. So to do that, I would subtract 3x from this side and subtract this side to be legal. So 2x's plus 2 is less than 15. Now you can combine these two steps if you want, once you're comfortable with that rule of order of operations. and say, all right, now I want my constants on the other side isolated. So 2x is less than 13. Now I want to know what x is doing, so I'm going to divide. But since I'm dividing by a positive, I do not have to reverse the inequality. So this is x is less than 13 halves. This is inequality form. This is set builder. For the set of all x such that x is less than 13 halves. Okay, then we can do graphical. And we would have a little number line like this. And here's my 0. And 13 halves is over here somewhere. And this is less than only, it's not equal, so you would not color the little dot in. So you're going to use a curved one of these and go this way. Or use a different colored pen. These are kind of easy to misinterpret because, is this round or is it square? All right. So this interval form actually makes it easier to tell as long, it's easier for people to write. So you always write it left to right. So your leftmost is negative infinity. Your rightmost is 13 halves. You cannot be equal to 13 halves, so it's round. And this is round. The infinities are always round because you never get to stop at a particular number like a million. You want to go to a million, I can go to a million and one. Or you want to go to negative 1 million, I can go to negative 1 million and one, negative 1 million and 45 or whatever. Sometimes students, and I applaud them, they make me chuckle. If their handwriting, like mine, sometimes leaves something to be desired, they'll write me a little note and says rounded, and I just laugh. It makes me giggle. It makes grading a little bit more lighthearted. So, if you're not sure that your teacher's going to understand whether you meant to square it off or make it round, tell them, all right? It might make them chuckle, and everybody needs a laugh once in a while. You do too. Maybe it'll give you a chuckle to write it, and it'll give them a chuckle to read it. Right. Now, this one's a little different. This one says less than or equal to, right? Now, this is not the English or. Okay, let's talk about that for just a second. So the English or is, let me see. A good example would be like when you were little and you'd go to the store and maybe your mom or dad took you or an adult or something and they said, you can have this or that, like maybe a piece of candy, right? You can have this piece of candy or that piece of candy. Now the English or says you need to pick one because you're not getting both, correct? And I don't know about you, but for my mother, if I took too long to think about it, I didn't get either one. All right. So, or in English means one or the other, but not both. Okay, typically. That's what we think of. In math, or means, they're both good. I'm fine with that. This one or that one, either one's fine. Okay, so in math, or means, they're both fine. Okay, that's how you get less than or equal to at the same time, because less than's good, well, or equals good. I could go with equals. Okay, so it's sort of like maybe picking a dessert, now that you're an adult, they go, do you want this one or this one? And you go, oh, they're both good. That one or that one, I'm good. All right, so it's not the strict pick one, or it's the, they're both good, or. All right, now here we go. So I am going to multiply by a negative 4 in order to clear the fractions. This is one of the things we talked about in the linear equalities in the previous video. So I'm going to multiply by negative 4 here and negative 4 here, because what you do to one side, you have to do to the other. This negative 4 would be canceled by the other negative 4 because negative 4 over negative 4 is 1. Every time I say cancel, I think of that one teacher I had that worked for me that if you said cancel, oh my gosh, she'd get so angry, and I just loved her to death. So if I had to substitute in her class, I was very careful not to use the word cancel. All right. Now, so here we go. Can't add 20 to 5x, but I can multiply. So negative 4 times 5x is negative 20x. And negative 4 times 20 is negative 80. Okay? All right. Now, do you see anything weird that should have happened between here and here? What do you think? Did we multiply both sides by a negative? We did? Okay, so what do you have to remember to do? You have to remember to reverse the inequality, even when it's that early on. All right? So even if it's early on in the problem, not just at the last step, okay? If it's early on in the problem, then you have to remember to reverse the inequality. So you might want to consider taking that step where it says if you multiply or divide by a negative, you have to remember to reverse the inequality. You might maybe make that like the first thing at the top of the line. As soon as you see an inequality, you go, okay, wait, don't forget, if you multiply or divide by a negative, you have to reverse the inequality. You need to pick where you put it in your list, all right? Now, so let's talk about this. I have two choices. I can put all my x's over on the right side, or I can, and then I'd have to read backwards from right to left, or I can put all my x's over on the left side and they'd be positive. You want to go for positive? All right, so let's add 20x to both sides, because that's the opposite of subtracting 20x. So you'd have 22x plus 5 is greater than or equal to negative 80. Right. So then if I want my x's on the left, I do not want my numbers on that side, my constants. So I would have 22. For some reason I can't make two 2's the same. 22x is greater than or equal to negative 85. So x is greater than or equal to negative 85 20-seconds. That doesn't reduce. All right. So this is inequality form. Set builder form. For the set of all x such that x is greater than or equal to negative 85 over 22. All right, graphical. Usually your teacher will demonstrate for you, what kind of, whether they want, little circles colored in or not. So in the past, since this is greater than or equal to, you may have had a little circle you would color it in because it says equal. This little equals right here says to color it in. This one and this one. I tend to think of it because I make up stories with my math stuff and it kind of keeps me entertained while I'm doing it. All right. Is if I can be equal to it, then I can actually stand on it. Okay. So, and not fall through, right? Like a manhole cover. Okay. I can not fall through. So, it would look like this if you're going to use the newer notation. And you'd have negative 85 over 22. And this would be squared off. Again, this sort of makes you think you could stand on it because it's got a little ledge. If you'd had it rounded and tried to stand on it, you just slide off. All right. So sometimes little visual images like that help me to keep track of what I'm doing. If little visual images like that help you, rhymes, anything like that, repetition helps you, please do that. Okay. I had a student one time and her significant other made fun of her for doing this. And I was like, don't tell him you're doing it. Okay. And I said, you don't have to tell him how you remember this. And it doesn't matter if you get the answer right. It doesn't matter what he thinks. And it doesn't, and he shouldn't be making fun of you in the first place. But, neither here nor there. But it is up to you. Your teacher doesn't know what you're thinking to do this. If you have a silly way, quote unquote silly way to remember it, I'm all for that. Please share it with me. I'd love to pass it along. All right. So this is graphical. I love sharing silly things because they make you smile, and you will remember the silly thing more than you will remember my logical description. That's what my students tell me. They say, "Oh, I remember all your stories." Okay. Now, so for interval form, you always go left to right. So my leftmost viable point is negative 85 over 22. I have 25 over here. Okay, over 22. And I go as far to the right as I care to go, all the way to infinity. And remember, infinities are always rounded off. And we have that number, all right? Now, we're going to do another problem or two, and then we're going to talk about some of the little unusual ones where you have all real numbers or no solution. And we're going to get started here in just a second. All right, so let's try 1/5 x plus 2/5 x minus 1/2 times x plus 3 is less than or equal to 3/10. Now, while it's true that 1/5 x and 2/5 x are like terms, not only are they both counting x's, but they even have a common denominator, and we could go ahead and add those together and say that's 3/5 of an x. I want to practice one more time this concept of clearing the fractions within an entire equation. It can be an equation that's got an equal sign or an inequality. So the least common denominator between the fifths, the 1/5, the 2/5, and the 1/2, and the 10th on the other side is 10. So the least common denominator is 10, and we're going to multiply both sides by 10. Now, if you're one of those people that likes to cross out things and cancel and as you go, then there's a slight danger where you could say, all right, this 5 cancels into 10, leaving me 2, and 2 times 1, because the fifth is gone, x is 2x, but then attempt to multiply this next term by just the 2. If that, you can see, is going to be a temptation for you, then what I suggest you do is you actually take the extra step and write 10 down next to each item so that you can slash through to your little heart's content and you'll still be okay. So this 5 goes into 10 twice, and 2 times 2 is 4 x's minus. Now, this 10 is only applying toward this 1/2. So 10 times 1/2 is 5. The 10 does not apply to the x plus 3 as well, because I would need to have a plus or minus sign in there for it to keep continuing on over to multiply. So I have minus 5 times x plus 3 is less than or equal to, and this 10 cancels that 10 and leaves you 3. And like I said earlier, if your teacher has this thing about not saying the word cancel, you can say reduce or divides into or something. Now, see how all the fractions are gone? This is why they call it clearing the fractions, because there's no fractions left. That makes it a substantially easier problem. I did multiply both sides by a positive, so I don't have to reverse the inequality or anything. So let's go back to our steps and go, all right, so I need to simplify the left-hand side. Now 2x and 4x, I could go ahead and add, but before and this is a matter of choice on your part, I'm going to hit and go over here and multiply, because scanning it quickly, you can see that inside the parentheses, you can't add 3 to x. So you would come out and multiply, and that would be minus 5x minus 5 times 3 is a minus 15. And in the rule of order of operations, you would start with the parentheses and work your way out, but you'll find out that as you go along, if you have some kind of bits and pieces hanging on, kind of like this part and this part, then you could do those as you go across. But you have to have sort of a gut instinct for it. So if you're not there yet, then start with that rule of order of operations and follow it just as closely as you can. All right, and I don't have anything to simplify on the right, so I'm going back over to here. 2x's plus 4x's is 6x, minus 5x is x, minus 15 is less than or equal to 3. So I have simplified the left, simplified the right. I want my x's isolated on one side, so that means I do not want the minus 15 with them. So I do the opposite of to subtract 15, I add, and I must add 15 to the other side to be legal. So x is less than or equal to 18. And that gets everything done. We don't have to multiply or divide by anything anymore. So life is good. Now, this is inequality form. Again, we could do the set builder version of inequality, which is for the set of all x such that x is less than or equal to 18. We can graph it. So here's 0, here's 18. I want less than or equal to. So depending on whether you're using the dot or the brackets, a lot of it depends on, are you doing computerized homework and what your teacher wants. So I want to include the 18. So if I was using a dot, I would color it in. And I want the x's that are less than or equal to 18. And those go this way. If I'm using the version that doesn't use the little dots, I would have the squared off parentheses or bracket, and then I would go to the left this way. And it's probably easier for this one to be seen if I do it like that. And if I want inequality notation, you go left to right. So your leftmost point is negative infinity. Your rightmost is 18. This is squared off. This is round. Okay. This one's kind of a little bit different. Let's try 6x minus 2 times 2x plus 3 is less than or equal to 4x minus 5. So let's simplify the left. I'd have 6x. I'm going to distribute this negative sign. So minus 2x minus 3 is less than or equal to 4x minus 5. Keep simplifying the left. 6x's minus 2x's is 4x's. Nothing to simplify on the right. Now I want my x's isolated on one side. So you could subtract 4x to get, your original intent is to get them on one side, but when you do that, notice that your x's cancel, go to 0, and you have this situation. Now, depending on how comfortable you are with negative numbers, let's look at this. Is negative 3 less than negative 5? Not really. Okay, if you're thinking about your bank balance, negative 5 is even less money than negative 3. So negative 3 is not less than negative 5, and it's not equal. If you're not comfortable with negative numbers yet, let's just keep going and say, okay, I don't want my 3's on this side. So I'd have to do the same thing to the other side. And I'd have, is 0 less than or equal to negative 2? And that one, maybe you're more comfortable with that. Is 0 less money than negative 2? No, 0 is no money, but negative 2 is even worse. All right, so this is a false statement. Both of these are false. And for some of you who are really comfortable with variables, you may recognize that this is a false statement. How can you take an x, multiply it by 4, and subtract 3, and have it be less than taking this x, that's the same x, multiplying by 4 and subtracting 5? So somewhere in here, you would recognize this as a false statement. And so what it's saying is what you're looking for does not exist. So there is no case where this left-hand side is less than or equal to the right-hand side. So you would say this is no solution. So in English, you would write no solution. And in like mathematical symbols, you would write 0 with a slash through it. Now let's talk about that for a second. Military people write this for 0. Computer programmers do that sometimes too to keep it separate from the letter O. So if you're in the habit of doing that for your 0, like if you were trying to write 750, you wrote 750 with us, that's going to be a hard habit potentially for you to break, but you cannot use that for 0 in a math class because this does not mean 0. This means no solution. All right? Does not mean 0. So don't use that. If you were trying to say x is 0 and you put a slash through it, you're basically saying x is no solution. So be careful. All right, on we go. So how about this one, which is sort of like the other end of the spectrum? So what if we have 2 minus 6 times x plus 1 is greater than or equal to 3? Negative 7 minus 2x. Okay, simplify the left. Can't add 1 to x, but I can multiply, so 2. You don't go 2 minus 6 is minus 4. That's where this up here where I said if you're comfortable with these things, you can add these two together because they're not like this part yet. But down here, if you had said, all right, let's take 2 and subtract 6, you can't do that because you're multiplying what's in here by negative 4 now instead of by negative 6. So you can't do that. So we have 2, negative 6 times x, negative 6 times plus 1 is greater than or equal to, this is actually supposed to be 7, but it doesn't look like it. So you would have 3 times a negative 7 is negative 21. 3 times a negative 2x is negative 6x. So let's do the thing again and get our x's on the left-hand side. Really and truly, I guess we should have, in the grand scheme of things, maybe done our 2 minus 6 first, but again, you'll get used to the fact that once you get comfortable with the fact that this 6x is a different term than this 2 minus 6, you can work them separately. All right, so 2 minus 6 is a negative 4. And over here, these cancel. And so I have negative 21. Now, how often is negative 4 greater than or equal to negative 21? Now, remember that or means either one. As long as either one is good, the whole thing's good. All right? So, because I'm not picky. If it's at least greater than, I'm fine with that. It doesn't have to be both, right? So, negative 4 is always greater than negative 21. Again, if you're like, I'm not seeing that, okay, you'd have 0 is greater than or equal to negative 17. So how often is 0 better than negative 17? All the time. Okay, so this is true. And when something is always true, instead of it being no solution, it's all real numbers. Okay, any value for x would make this a true statement. It's true that the left-hand side is always going to be bigger than the right-hand side. Okay, and if you're doing it in interval notation, it looks like negative infinity to infinity, saying you can pick any number you want between negative infinity to positive infinity, and it's going to be good. Now, when I was taking math many, many years ago and was just first learning it. So I always tease my students and say that was way before electricity, back in the horse and buggy days. And I think some of them actually believe that, but it wasn't that long ago. Right? But when they sometimes give you two of these to do at once, and I always used to sarcastically tell myself, that's just the teacher getting you to do two problems for the same 5 points, that maybe this problem was worth 5 points. So now we're going to do two for the same 5 points. So I'm going to work twice as hard. All right. But sometimes they do combine these and say, hey, I've got two situations that I want to have you consider, and I want to see what the kind of group total summation answer is. So we're going to work these as if they're not related to each other for a minute, and then we're going to graph them and see what happens. All right. So working with the equation on the left, we go, well, I can't simplify the left-hand side. Can't simplify the right-hand side because there's no like terms. Let's get our x's on the left. So 7x's minus 9x's is minus 2x's. Plus 1 is less than 8. So then I want to get my constants on the other side. So negative 2x is less than 7. And now I want to know what x is doing. So I'm going to do the opposite of what negative 2 is currently doing, which is to multiply. So I'm going to divide. Now when you do that, remember when you multiply or divide by a negative, you have to reverse the inequality. And no one's going to remind you of that but you. All right, let's look over here. On the left-hand side, I can multiply through by this 5. So 5 times x, 5 times 2 is less than 4x minus 6. I want to get my x's on the left, just because it seems to be where people like to have them. And I kind of second that. So 5x's minus 4x's is x, plus 10 is less than negative 6. I want to get rid of the 10. I don't want it on the same side as my variables. So the opposite of add 10 is to subtract 10. So we would have x is less than negative 16. So these are my two situations. So here's 0. So negative 7 halves would be, over here, let's say. You don't have to draw these to scale. And this would be negative 6. So looking at this one, I want the x's that are greater than negative 7 halves. That would be this way. And we would round it because it's not equals to. And negative 16 is here. It's also less than only, as opposed to less than or equal to. So it would look like that. Maybe this will make it easier to see. And in inequality form, it would look like negative 8 is less than negative 6. Negative 7 halves to infinity. Because you would start here, go to negative 16. I keep wanting to write 6 instead. There you go. Moving on to the next problem. 2x minus 6 is less than or equal to 3, or 3x plus 5 is greater than negative 4. So here we go. Nothing to simplify on the left. So I'm going to add 6 to both sides. 2x is less than or equal to 9. Divide both sides by 2. X is less than or equal to 9 halves. You doing okay? I kind of skipped a little bit of narration steps in there, but I think you're ready. If not, already progressed past that point. All right. So I can't simplify the left or the right. I'm going to subtract 5 from both sides. Get 3x is greater than negative 9. Divide both sides by 3. X is greater than negative 3. So when I graph these, Here's negative 3. I want the numbers that are greater than negative 3, that would go this way, and the numbers that are less than 9/2 or equal to, so they'd be squared and go this way. I don't know if you can see those really well, so let me try something else. So you would have 9/2 colored in and going this way, and negative 3 left open and going that way. Does that help you to see a little bit better? All right. Now, so I put these together and try to look at where like here, let's look back here. I only wanted these numbers on this end and these numbers down here. So I had two separate sets of numbers, right? And what joins them together is this union, which is actually the math version of OR, saying both are fine. Okay? I should have maybe mentioned that before, but this U shape right here is called a union and stands for OR, saying either one of those is fine. Okay? I like them both. Now, this case, do you see how every single number on the number line is accounted for? So from 9/2 down, all of these numbers from here to here are accounted for. Now, this negative 3 is left open for this one part, for this right equation right here. But this negative 3 is covered by this equation right here. So this one picks up all the numbers that are above from here to here. So all the numbers are accounted for. So this says all real numbers are included to solve this setup. Okay? Let's try just two more and then a little story problem. If they have an OR problem, they also have what's considered an AND problem. So that if you had something like negative 5 is less than 5 plus 2x, and 5 plus 2x is less than or equal to 11. So you can combine these by seeing this kind of common binomial there, okay, but common phrase, common set of terms. So you can combine those by just writing this here in the middle. And this is a compound inequality that originated as an and, but they started writing it as just this. And a lot of books don't even do the ands anymore. They just do this, but your book may have an and, all right? And if it's an and, I'll show you what that does in just a second. So what this is instead of having two sides to your equation, you have three. So here's your first side, here's your middle, and here's your right-hand side. It's kind of like a cookie, okay? So maybe like an Oreo. So you've got your left-hand side, your middle, and then your right-hand side. So what you do to one side, you do to three sides, not just to both sides. You go, okay, what I do to one side, I have to do to all three sides in order to be legal. And you start here in the middle. You always start where the variables are. And look, okay, so I can't add 5 to 2x. So, well, okay. Now, what I could do is I still want to do this thing where I want my variables isolated. I no longer have a left side and a right hand side. I have three sides, but I still want my variable isolated. So let's get rid of the 5. So we would subtract 5 from three places. So negative 5 minus 5 more is negative 10, is less than 2x, is less than or equal to 6. Doing okay? All right. Now, same principles as before. I want to know what a 1x is. I don't want to know what 2x's are doing. So this is 2 times something, so I'm going to divide. And what you do to one side, you do to all three sides. So negative 10 divided by 2 is negative 5, is less than x, is less than or equal to 3. So what this does is you are literally sandwiched between negative 5 and 3 to where you would have, if you were doing the little bubble things, it would look like this. Where are your x's? Somewhere in this area. Or it would look like this. Squared on this end, rounded here, and then you would join these two together. So in a different color, it would look like that. All right. So that if you had this and here, what would have happened is you would have said, okay, 5 plus 2x is less than or equal to 11. You would have subtracted 5 from both sides. 2x is less than or equal to 6. X is less than or equal to 3. Then you would have subtracted 5 from both sides here. 2x is actually greater than negative 10 reading backwards. So divide both sides by 2. Negative 5 is less than x. Okay. And when you graphed this, you would have had x is less than or equal to 3. So we've gone this way, right? And this one says negative 5 is less than x. But to graph it, it might help you to switch these around. And remember, if it's pointing at the negative 5 before, it has to point at the negative 5 when you switch them around. So I want the numbers that are negative 5 and greater. But now instead of wanting all of it, because or said, whatever you have is fine. I like them all. Okay. And says, I want to know what they have in common. So and is what's in common. And that would be this section right here. That's where the overlap is. That's what they have in common. So it's what they have in common or sometimes considered an overlap. All right, let's do one more of these. So if you have 1 is less than or equal to 4x minus 5 over negative 2 is less than or equal to 9. And you can already see it coming, can't you? So I want to clear the fractions, so I'm going to multiply everybody by negative 2. So what I do to one side, I am now doing to 3 sides. So negative 2 times 1 is negative 2. Whoops, let's hold off on that less than or equal to for a minute. This negative 2 is going to cancel this negative 2, and I would have 4x minus 5. And negative 2 times 9 is negative 18. Now I multiplied by a negative, and what is it that you have to remember to do when you multiply or divide by a negative? At any point in an inequality, you have to reverse the inequality. All right, now here we go. So let's add 5 to both sides, or all 3 sides. So I'd have 3 is greater than or equal to 4x is greater than or equal to negative 13. And then you divide all by 4. I'm dividing by positive, so I don't have to reverse again. So 3/4 is greater than or equal to x is greater than or equal to negative 13/4. Now to get these graphed, usually people aren't very comfortable graphing greater than things where the x is. So what we're going to do is to switch these around. So negative 13/4 x and 3/4. But remember, what happens is in this case, this one that goes with the 3/4, this part right here, it's pointing at the x. So it has to still point at the x. When you look at this one, with the x and the negative 13/4, it was pointing at the negative 13/4, so it has to point at the negative 13/4 again. So you're not flipping them because you multiplied or divided by a negative again. You're flipping them to keep the context of what is greater than the other one to be true when you switch them around. if x is greater than or equal to negative 13/14, here's reading backwards. X is greater than or equal to negative 13/4. I think I said 14th. Negative 13/4. And on this one, x is less than 3/4, reading backwards. Here's x is less than 3/4. So in interval form, it would look like this. So here you go. All right. So let's do a little story problem. What if you had a situation and we were talking about cost and we talked about revenue? So you were in a manufacturing situation and you have a certain cost per unit of production and you bring in a certain amount of revenue when you sell that. So let's say your cost function was 2x plus 100 and your revenue that you bring in is 6x. So everyone you sell, let's say you make $6. Okay. And the cost is $2 for each one that you're building, and you have $100 cost. Maybe that's for like your electricity, all right, or rent payment or something like that, or some fee that you're gonna. It's just a one-time fee. It's not per unit. Okay, it's just a set fee, no matter how many you make. So that if X was 0 and you didn't make any, you would still cost you $100 just to have the business. All right. Now here we go. So what if they're wanting to know when is the revenue going to be at least as much as the cost? So what they're looking for is, in a sense, how many do I have to sell in order to break even? But what I really want to do is to make a profit. So when is my revenue going to be at least what it's costing me to produce, and making more than that just makes a profit from everyone in addition to that point. So you're saying, where is the revenue greater than or equal to the cost? So the revenue is 6x and the cost is 2x plus 100. So we would do our whole thing, simplify the left, simplify the right, get our variables on one side. So 4x is greater than or equal to 100. Then we want to know what x is doing. So x is greater than or equal to 25. So what does that mean? If I sell 25 units, I break even. For every unit that I'm going to make above that, I'm actually going to make a profit. So 25 units, I break even. So the break even point is 25 units. I have to sell more than 25 before I start actually showing a profit. All right. Now, what if the cost function, what if the revenue was still 6x? I still only sell them for $6 a piece, but my cost function was higher because I'm using more exotic materials or something, okay, for each one. Then again, when is the revenue greater than or equal to the cost? So 6x is greater than or equal to 8x plus 100. Subtract 8x from both sides. Negative 2x is greater than or equal to 100. Now at this point, you're like, wait, what's the negative 2? All right, and when you divide by negative 2, you'd have x is less than or equal to negative 50. Okay, how do you make equal to or less than negative 50 of something? You don't make anything at all. Okay, so your best bet in this case is that your cost is too high, and you would be better not to make anything at all than to make some and get $6 each one, because you're going to be making no profit at all. You'll be losing money. Okay, so this says there is no time, okay, where you're going to break even or make enough to make a profit. So there is, no solution, no break-even point. You should not make them at all. This is a no-win situation. So this would be a venture you wouldn't want to start up. Okay. All right. So I hope that helps. That was kind of a long introduction to inequalities, but I think there was a lot of um, little tiny subtleties in there. So next we're going to do absolute value inequalities and equalities, and then we'll start getting into a little bit more of the graphing and then the factoring and then the quadratics and all that neat stuff that actually becomes the meat of the college algebra class. So I'll see you at the next video.